Connect, collaborate, discover. Transforming research and education networks to the power of N. I'm Kate Winn, Head of Executive Communications for the Network Infrastructure Group at Nokia. And this is Reconnect, where we dive into today's finest research and education networks in the company of some of the great minds behind them. Today, we're talking about quantum-safe networks, particularly the successful completion of a QSN proof of concept by Nokia and HellasQCI. HellasQCI is a consortium led by GRNET, Greece's national infrastructure for research and technology. With GRNET connecting more than 150 organisations across 50 cities and hundreds of thousands of users, the trial's use of both classic and quantum physics for key generation is an exciting sneak preview of QSN-enabled critical infrastructure security across Greece in the years to come. To tell us more about this proof of concept trial, I'm joined by George T. Kanellos, Assistant Professor in the Department of Informatics and Telecommunications at the National and Kapodistrian University of Athens. With us is also Marta Buffa, who is an optical network design and system engineer at Nokia. So, welcome to you both. George, I'd like to start with you, if I may. Tell us a little bit about what role your institution, NKUA, plays in the proof of concept.
NKUA, the National Kapodistrian University of Athens, is operating as the technical coordinator for the HellasQCI. I'm personally the technical coordinator for the project. And in that sense, we led the efforts in designing the overall architecture for the HellasQCI quantum networks. Now, together with GRNET, we decided to launch this proof of concept network. It was an effort to identify, validate the overall architecture over a real implementation. And this is how Nokia came as a prime and won this RFI to help us implement this proof of concept of the HellasQCI architecture.
Okay, and tell us a little bit about the results of the proof of concept, and especially why the findings are important to you.
Well, that's the most interesting part of the implementation of this proof of concept. What we aimed to do was to implement a small scale of the overall architecture. However, it was quite ambitious, so it would bring some features that have not been demonstrated previously in quantum network implementation. This proof of concept has to use a hybrid scheme that may consume classical and quantum keys together to provide a backward compatibility with legacy or existing systems, and also provides an immediate certified fallback solution in the case that the quantum networks are not available. The second aspect is that the security management system that Nokia provides operates as the orchestrator that combines the needs of the classical networks in terms of encryption requirements in the different nodes, together with orchestrating these needs in the KMS, in the key management system of the quantum network. The third interesting aspect was the fact that in our explicit demonstration, we implemented a ring network of 3 nodes, but with only using 2 QKD links. And in this way, forcing the KMS to properly balance the available quantum keys across the different nodes at all time.
When do you think we will see deployment of these quantum-safe networks that use both classic cryptographic and symmetric quantum key distribution? Yeah. I know that it's a bit of a loaded question, but what do you think? What would be your guess?
Well, that is a good question. And in fact, as it happened with all new technologies, it started with excitement and enthusiasm all around. And in the very beginning, it was creating very high expectations. I think that there is an increased awareness on the needs to migrate towards the quantum safe solution. And I also think that Nokia's approach to implement a hybrid scheme in combining classical keys with quantum keys relaxes the stress for transitioning directly into a brand new technology, in that sense bridging the gap. Overall, I think that we will get there in a few years, not to mention the fact that there is also significant progress in the certification of these technologies that is absolutely essential when, in order to bring them into the operational field.
Marta, I'd like to turn to you, if I may. We've heard a lot about the looming threat of bad actors and the potential to use quantum computers to hack into previously secure networks. Tell me, how real is the threat?
Quantum computers have the potential to break certain encryption algorithms that are considered secure today. So now it's the time to start the quantum security journey and prepare for the harvest now and decrypt later attacks, which refers to a kind of attacks where bad actors can store encrypted data from target organizations today, anticipating that data that can be decrypted later when quantum computing reaches the maturity level capable of rendering some existing cryptographic algorithms obsolete.
What makes a quantum safe network?
The basic components to ensuring the protection is achieved through multiple mechanisms, including, for example, data encryption, strong key generation, management and distribution, independent certification. So how we create, how we distribute, and how we manage the keys. Just ensuring that the application layer is protected is crucial, but not sufficient to achieve a truly quantum safe network. As Nokia, we believe in a defense-in-depth approach which encompasses all layers of the OSI model. By doing so, even if one layer is compromised, the other layers continue to provide protection and creating a resilient security architecture.
And while we're into the way that one builds a quantum safe network, Marta, there are different methods for distributing quantum safe keys.
Sure. Distributing quantum safe keys involves a combination of methods. There are asymmetric cryptography and symmetric cryptography. For the first method, there will be new kind of algorithm which will replace the algorithm that underpin today public key infrastructure. However, standardization, further testing, and benchmarking is required to fully understand the behavior in different computational environments. The second method, pre-shared keys, uses symmetric secret session key for both encryption and decryption of data. And these ensure confidentiality and integrity of the information, as the same pre-shared key is used between the communication parties. The pre-shared keys can come from pseudo-random number generators, but it's a deterministic and predictable output, or with a true random number generators, which is classical physics process based on an output which is unpredictable. The Nokia classical solution involves the use of a centralized management approach based on a single point of trust, where the pre-shared keys is computed off-board in a single physical location. And this method is certified and field-proven. Similarly, pre-shared keys can also come from quantum physics and distributed through a quantum key distribution networks, which is exactly what we have done with HellasQCI and GRNET. Here, the security can be demonstrated with the theory of quantum mechanics, and this method is built on top of the automated pre-shared keys based on classic physics. And the main advantage is both to provide a very robust and resilient solution.
George, I'd like to come back to you, if I may. Would you say that research and education networks are particularly suitable as frontrunners in this kind of work and driving it forward?
I think that research and education is indeed the field to start with. And in that sense, NRENs are obviously, the best possible choice for accommodating these first proof of concept networks or even first deployments of the operational networks. Everything in the technology sector has a learning curve, and we need to understand this and expect that, things will evolve, but it takes time until they mature enough to hold critical operations.
So I wanted to ask you both, what's next for your partnership?
I'd like to extend this beyond this partnership on the proof of concept. I'd like to refer to the targets of our project in Greece, the HellasQCI, which is obviously expanding the network in terms of physical locations and nodes to be added. We also need to expand or demonstrate or put it under test with the various client services coming from the different sectors. And we see a new technology that is coming, post-quantum cryptographic scheme, that have recently been released as a recommendation from the EU, and would like to align to see how we integrate these technologies into our overall architecture. So these are the macroscopic ends. And of course, last but not least is the integration or expansion or connection with a pan-European quantum network. So this is the bigger picture for the HellasQCI. When it comes to expansion of the proof of concept, we would like to see or put in test aspects related to that. So how we expand in the number of nodes, how we expand to accommodate more services and clients. Obviously, how we can connect with different domains or different networks. And would very much see our proof of concept expanded and potentially integrated with a pan-European demo.
I think that the partnership has been successfully so far thanks to a structured framework and collaborative approach leveraging Nokia world-leading network experience. So Nokia is looking forward to expand the partnership for the HellasQCI project, supporting GRNET and UK, developing new use cases, introducing new potential partners to augment the HellasQCI capabilities, so jointly driving the message of quantum-safe connectivity in public conferences and thus disseminating the positive outcomes within the EuroQCI community and possibly behind.
That's great. Thank you so much to you both. I'm afraid that's all we have time for today. But I'd very much like to say a very warm thank you to our guests, George T. Kanellos and Marta Buffa. I'm Kate Winn, and thank you for listening. It's always amazing to see how customers are using networks to unlock new research and discoveries. If you'd like to learn more about the RENs we've discussed and the technologies behind them, visit our website. Next time on Reconnect.
We are in the early stage of optical sensing area using already deployed optical fiber communication infrastructure.
And the coherent state of polarization detection, can have a very, very big impact in building the network sensing all over the world.
But all in all, the benefits of using sensing for monitoring the environment and climate changes are huge, both for mankind and also for planets actually.